Hey everybody, hope that you guys are doing great. We're going to be going through our notes on the third target dealing with radicals, and the goal here is that we're hoping that we can solve radical equations, and then later on there's a second little checkpoint here of making sure that we don't have what's called an extraneous solution, and so we'll get to those closer to the end of the notes. But a radical equation is just any equation that has a variable in the radical sign, which you should know that that just means the root, or we could potentially have a variable with a rational exponent, meaning a fractional exponent. So if you are looking through the questions, they will always have an equal sign because equations are what we will solve for our variable. And you will have kind of these different setups where x is trapped underneath a root, or x is trapped inside of a group with a fractional exponent. So those are our formats for every single question on this notes. If we go ahead and look at the first question, I realize some classes may have done this already, but it's not bad to review. We have a square root. 5 and x is inside, and then also a plus 1, and we're equal to 6. And the bad part of this is that we need to get the variable out of the square root. And so in order to do that, we're going to square that side. You have to square the whole side in order to get rid of the square root. They cancel each other out, essentially. But we don't get to do that without squaring the right. That's pretty easy to do. 6 squared is 36. But what happens to the other side? Do we get 5x plus 1 by itself? Or, as we've seen before in prior chapters, do we get the absolute value of that side? And it's kind of interesting. So I'm going to go ahead and bring in Desmos here really quick to figure out if we need absolute value bars or not. So firstly, I've typed in exactly what our work has. We have a square root, and then we are squaring that square root. And if I turn that on, you would expect to see an absolute value function if we're going to use absolute value bars here in a second. But surprisingly, we don't have that. If I zoom out, some people want to say it's a line. Other people want to say that it's a ray. It's not really a line because it doesn't go on forever. Ray is sort of maybe an idea of this. But if you turn on the absolute value of 5x plus 1, notice that's what's inside the square root. And if I turn this back on, weirdly enough, this is half of an absolute value graph. So what's interesting, if I just take the order and I switch the order, notice up here I have the squared inside the square root versus the squared on the outside and the square root inside. That order really plays a big difference. If I turn that on, you can see these two graphs are the same graph. So squaring something first actually can work with negative or positive numbers. Both are fine to square because you just multiply a negative times a negative or a positive times a positive. But when you square root first, you only really want to consider the positive numbers, because if you square root negatives, that's when imaginary numbers would come into that situation. And so we don't have to have absolute value bars in our work because we're only considering the positive case, the right-hand side of that absolute value function. So that's really nice for us because now we just get to go ahead and solve like business as usual. And so we subtract 1, we end up getting 5x equals 35. Now we know how to get rid of the 5 by dividing. And in the end, x is equal to 7. If you weren't sure about this and you wanted to just double check, you can always take this value and substitute back in for x right there. 5 times 7 is 35. Add 1 to that to make 36. Square root 36, and you end up with 6. The calculator would also work. So if we're going to jump into number 2, number 2 just has a little bit of extra stuff to isolate the root. That's always your goal, is to get that root by itself. And so we're going to add 10 right away. We get square root of 2x plus 1 equals 5. Now comes the tricky part of we have to get rid of the square root by squaring. And we square both sides, the left side and the right side. No need for absolute value bars. We just have 2x plus 1, and then 5 squared is 25. Going ahead and starting over in the order of operations, subtracting 1. 2x equals 24, and then divide by 2, In the end, you get x equals 12. I'll make sure to show the rest of my work, though, just in case you need it for your notes. So you can see it's kind of straightforward in terms of what we are trying to do. The goal is to get down to this x equals solution. That's what solving means. And so you just have these kind of steps to follow in order to get there. Let's go ahead and let's take a look at question number 3. You'll notice the type of root here is a little bit different. It is a cube root, but similar to how squaring something, raising it to a power of 2, undoes a square root, we can get rid of a cube root. We just have to cube it, raise it to the 3rd power. So the higher the index on your root, the bigger the dynamite needs to be to blow it up when you come to powers. Still no absolute value bars. It wouldn't make sense in this case anyway because it's an odd root, but we get x plus 2, and then 2 to the 3rd power, 2 times 2 times 2 is 8. Going ahead and subtracting that 2 from both sides, we end up with x equals 6. And this should make sense if you are a answer checker. Put 6 back in, 6 plus 2 is 8, and we know the cube root of 8 is 2. Now if you had thought that there were absolute value bars in this, and you go ahead and do the second version, and if you check that second answer, you'll notice that it does not make the correct amount. I think you would probably get negative 10, and negative 10 plus 2 is negative 8. The cube root of negative 8 is not positive 2, and so that's why we don't have absolute value bars in these types of questions. 4 is similar to number 3. If you're thinking about steps or maybe need a little bit of help, dividing by that negative 10 right away is the best thing to start off with. And so you isolate the root, the cube root of 3n. Not really a big deal that it's a different letter. N behaves the same as x. They're both variables. Negative 90 divided by negative 10 is positive 9. And then getting rid of the cube root by cubing to the 3rd power there. 9 times 9 times 9 is fairly big. If I remember right, it is 729. And then you have 3n dividing by that 3. I think n in the end is 243. Hopefully not too hard. The next group of problems are really where things start to shift a little bit. You notice we don't have roots. We have these fractional exponents as mentioned up above. And so maybe the easiest way to start thinking about this is one method. It's not going to work a ton, but it's handy to maybe start thinking, what type of root are we really dealing with in problem number 5? It has 12 minus x grouped together to the 1/2 power. And if you remember, 1/2 power means that is a square root. And inside that square root would be the 12 minus x group. If that's equal to 4, well, this is very similar to the questions we were just doing where we square both sides. Sorry for that 2 exponent, it's pretty sloppy. 12 minus x, and then 16. Subtracting 12 from both sides, we get negative x equals 4. And it's key that you keep the sign in front of the variable there because dividing by negative 1 or multiplying by negative 1, both would do the same thing, gives you, in the end, x equals negative 4. Now I've left all this space off to the right because I'm going to show you the way that we're going to do this normally. It's not always easy to change things into roots. It worked pretty nicely here because I had a nice fractional exponent. But if you look at number 7, 3/5 is there, 1/3, maybe you could deal with that 1/3, but like 3/2, sometimes they get pretty unwieldy. And so what we're going to do is solve using a second method. So I usually like to take my 12 minus x and the 1/2 power and give it a little bit of breathing room because we're going to annihilate, we're going to get rid of that 1/2 exponent here in a moment. And the method that we're going to use to get rid of this is canceling out fractions. So if that fractional exponent is 1/2, well, what will annihilate 1/2? Its reciprocal, which is 2 over 1. Now this is just my convention. I usually put brackets around it because we already have a set of parentheses, and so brackets just denote that it's a bigger group of things. So I'm taking that whole group, raising it to the 2 over 1 power. And don't forget that we're going to have to do the same thing on the right. And so raising that 4 to the 2 over 1 power is just essentially squaring the 4. And so I get 4 times 4, which is 16. If you like, you can cancel those 2's out, and you can cancel the 1's out, but you're left with 12 minus x. And you can probably see some relationships between those two steps. Going ahead, subtracting the 12, it's the same work. Negative x equals 4 divided by negative 1 divided by negative 1, and we get there. So both methods yield the same answer, but the second method of canceling out our exponent using its reciprocal, raising it to the reciprocal power, that is going to be the best thing to get rid of gross, yucky fractional exponents. Problem number 6 has a little bit more in front. It's kind of clogged up with that 2. And so that 2, which would, technically kind of be a stretch if you were to picture this on a graph, we just get rid of it by dividing. Okay, those cancel out. And so now we have that group of x plus 6 to the 1/3 power that is isolated. Keep in mind, a little bit of space is helpful. 12 over 2 is 6. And the reason we have that space in there is because we're going to bracket around this. We're going to take that whole side to the 3 over 1 power. So we're raising it to its reciprocal. And that's the same thing as just 3. So once those cancel out, and we're left with x plus 6 all alone, we just need to figure out what 6 to the 3rd power is. 6 times 6 times 6, 216. Subtracting that 6 gives us x equals 210. It is kind of fun. If you are ever in need of some excitement in life, you can take 210 and put it right back in for x. And if you type that in your calculator and press enter, it should give you 12, which is great. Great habit to get into. Problem number 7 follows that prior question fairly closely. We're just dividing by 3 now. So we have x plus 1 inside of a group raised to the 3/5 power. If you were going to try to make that into a root, it would be a 5th root, and then x plus 1 would all be cubed, and that's just not much fun to deal with. To get rid of everything and to just hassle it all out. 24 divided by 3 is 8. And so now we're going to go ahead. We're going to raise this to the reciprocal exponent, which is 5/3. That way the 3's cancel and the 5's cancel. Keeping in mind we have to do the same thing over here, 5/3. Now if you were good at R2, you'll remember that perfect numbers are kind of a big deal. 8 is perfect. It is a 2 times 2 times 2, 2 cubed. And the reason 2 cubed is probably a little bit beneficial here is because that 3 exponent will actually help cancel out the gross fractional exponent on the right side here. So if you wanted, you could do 2 cubed to the 5/3 power. So now when we go ahead, exponents raised to exponents, remember we're multiplying, which allows us to cancel out so much of what just made this question awful. Left over on the left side is x plus 1. Exponents are gone. They've multiplied to be 1. And then on the right side, 2 to the power of 5. That exponent's pretty important. 2 to the 5th power is 2 times 2 times 2 times 2 times 2, which is 32. Subtracting that 1 from 32 gives us x equals 31. If you're good at algebra, this should kind of be fun because it's more advanced algebra than you're probably used to doing. Exponents and roots have this really nice relationship where you can go back and forth and undo each other, and fractional exponents obey a lot of rules that should be hopefully easier to you now that we've learned about R2. Starting off number 8, we're going to go ahead and subtract 4 from both sides. That gives us 2, and then our group x plus 3 to the 3 over 2 power. And 58 minus 4 is 54. We got to go ahead and we got to get rid of that 2. So we'll divide. It would be wrong. Do not ever distribute into the group. And that's mainly because the exponent is the one who controls the group. Exponents are really powerful. Multiplying is not as powerful. So the way to undo multiplying is with division. That's what you want to do to isolate that group. X plus 3 to the 3 over 2 power. And leave a little space for our brackets here in a second. 54 divided by 2, that's 27. Which, 27, in my head, that's a perfect number. It is 3 to the 3rd power, which might come in useful here in a second. But let's bracket the left. And bracket's completely optional, but it helps you kind of tell the steps apart. And then 2 thirds. 2's will cancel, 3's will cancel. Just make sure 2 thirds is over on the right as well. And what do you know? The 3 from the 3 cubed and the 2 thirds, those will simplify down to be 1. And then same thing over here on the left, the 2's and the 3's cancel down. So x plus 3 is remaining, and then we have 3, the base, raised to the 2nd power, 3 squared, which is 9. Go ahead and subtract that 3 from it. X is equal to 6. Sometimes it is nice if you are not sure if you skipped a step or did something weird. Go ahead and check that. Put that whole thing in. If you type this left-hand side out, you should get 58 when you press equals on your calculator. So that takes us down to the last question. The only thing that's hard about this is that we have a 0.5 as an exponent. Not a big deal though, because 0.5 is just 1/2. And so changing that into a fraction makes this question actually very easy. We're going to go ahead and get rid of the 2 because we have to isolate things. Now, 5 over 2 is not as friendly as you might hope for, but it's still not awful. We're going to have x minus 2 in a group to the 1/2 power, and that's equal to 5 over 2. Some people will want to say 2.5, but we're going to keep it as a fraction here, just because when I get rid of this exponent by raising it to the 2 power, or 2 over 1, squaring fractions is not that big of a deal. Okay, as you know with exponents, you can just toss that exponent in to the numerator and denominator. Every single base gets distributed exponent to exponent with that 2. And so now I'm going to have x minus 2, because these have canceled out, equals 5 squared over 2 squared, which that's just 25 over 4, 25 fourths. Now if I'm going to go ahead and subtract 2, this is going to take a little bit of work because, remember, subtracting fractions, I need a common denominator. So not terrible, but this is essentially saying, hey, I have 25 fourths minus, I need to go ahead and multiply this by 4 and multiply the bottom by 4. And so 4 over 4 is a fancy way of saying 1. You aren't changing the amount. 8 over 4 is literally the same thing as that 2. But now we can go ahead and 25 fourths minus 8 fourths, talking in that language, x is equal to 17 fourths. And you don't need a calculator for that. Oh no, I made a mistake. I was looking back through because I didn't remember getting this on my first try through, and found it. If I'm subtracting 2, this really should be a plus 2. So we need to go ahead and we need to be adding. That is my fault, guys. Adding 8 fourths, 25 plus 8, makes a little bit more sense here. Let me erase that. 25 plus 8 is 33 fourths. Now, if you were checking your work, you would have found that we made a mistake because it would not have worked. We would have not gotten 5. Probably would have gotten something else random. So 33 fourths, glad that we caught that. Hopefully the front side of the note's not too big of a deal. To get rid of exponents, you raise them to the reciprocal exponent. To get rid of roots, you just raise them to the power that would cancel out that index. if you flip to the back page, this is where things get a little bit more interesting. Sometimes strange things happen in these types of equations, and you just need to be careful. And so we're going to start off with the definition that I mentioned on the front for extraneous solutions. And you can almost tell what these are going to be just from the word itself, extraneous. The first part of that word is extra. And so an extraneous solution is an extra solution that does not balance the original problem. And you have to make sure that it doesn't balance the original problem by checking your work. Now, we can kind of know that this situation arises when something happens through the problem. None of the front questions have extraneous solutions. And so it's kind of good to recognize when you might be dealing with extraneous solutions. So these fake answers, if you will, they can sneak in. They sneak into our problem when we go from an x to an x squared. Let me see if I can make that into an exponent. It would be nice. There we go. So when we go from an x to an x squared in our work, oftentimes we are introducing these extra values that might not work. I'm not saying that these extra values are always bad. Sometimes you could have a problem where you start with x, you get x squared, and so you have two solutions now instead of the one solution, and both solutions are fine. Okay? And so it's really important that you did the work correctly to get both of those solutions. Other times, one of those two solutions might be the bad one, so you need to check them both. And then there are cases where you would get extraneous solutions, you check both of these solutions, and both solutions are bad solutions. And so it's really, really important that anytime in your work you go from an x to an x squared, you have to check your two solutions. So we're going to see here in a second, this brings back all sorts of stuff from earlier in the year. If I go ahead and look at 10, the goal here is still to isolate that square root. Okay, you want to get square roots by themselves on their own side. That way you can get rid of them. And so the 5 is really bugging us. So I'm going to subtract 5 from both sides. And I get the square root of x minus 3 equals x minus 5. Now, just like the front, we're going to go ahead and we're going to square the whole left. But that kind of presents an issue on the right because I'm squaring two terms subtracted. And so squaring that group should mean something to you. It should mean that we are taking x minus 5 times its twin, x minus 5, and there's a four-letter F word that hopefully you are keeping in mind, an appropriate four-letter F word. First, outside, inside, last, FOIL. And so when we FOIL that, we're going to get x squared minus 5x minus 5x and then plus 25. Okay, if you kind of follow that out, that's how multiplying all of those terms kind of sorts itself out to be. You notice we started with x. There's an x in two spots, but it's still just x of that degree. Now we have x squared. It is at this step of distributing and foiling that I've introduced a second solution. We don't know if it's good or bad. We just know that now we have to check our work. So x minus 3 is what's left over on the other side. And now if I'm going to go ahead and collect like terms, group things together, we know that we're going to get x squared minus 10x plus 25. That's what these two guys combine into. If x minus 3 is on the left, let's have those guys join the party. So we're going to plus 3. We're going to subtract x. Oops. Sorry about that. And then subtract x from the middle term. So we're left here with 0 equals x squared minus 11x, that's what minus 10 and minus 1 do, plus 28. You may say, like, well, great. Now what do we do? Well, you kind of have to recognize what this is. And hopefully in your head, you're saying, ooh, boy, golly gee, that's a quadratic, Mr. Johnson. And you'd be right. So the question would be, how do we solve quadratics? And that's where the fun comes back in. We solve quadratics with any of those 4 kitchen tools, which could be square roots. Doesn't work here because there are too many x's. Could be factoring, which might work here. We'll have to test it out. Completing the square, and then the quadratic formula. So you get to choose any of those that are viable options. I personally like the x factor method because it's fast, and if you're really good at that, you can get your solutions pretty quick. So what we're doing here, remember a times c goes up top, the b value goes down below, and we need to multiply to get 28, and then add to get that negative 11. And I think if you have negative 7 and negative 4, those multiply and then add correctly here. Keep it in mind, you've got to divide those by 1. So this problem really says 0 equals x minus 7, x minus 4, if we write that out in factored form. And so our solutions, x equals 7, x equals 4. Now be careful, because if you just go ahead and you box that in and say, call it a day, you could potentially be circling an answer that would be bad, okay? Who knows? You could have just died there by circling those 2 numbers in. And so we need to check for extraneous solutions. Don't box things in until you've checked your work. So if we're going to go ahead, we can kind of do some of this in our calculator, or we could do it in our head. We're going to plug 7 in to where it was before. So 7 minus 3 is the square root of 4, plus 5. That should equal 7. So we get 2 plus 5, and that checks itself out. Okay? If I go ahead, let me erase the 7. And let's try 4. So I'm going to put 4 back here, and 4 right there. So 4 minus 3, well, that's 1. And then I have the plus 5 that's in the original question. And that should equal 4. So the square root of 1 is 1 plus 5. That's equal to 4. Well, heck no. That's not true at all. That would be saying 6 is equal to 4. So that's a big old 4 is an extraneous solution. It's one of these extra solutions that doesn't work. It does not balance the original problem when we check it. And so now I know just to box in the 7 and not the 4. So you can put a line through the 4 that tells me that you've checked your work and you know that it's wrong. It's not a true solution. It's an extraneous fake solution. And that's the process. The rest of these questions are very similar to the front. It's just oftentimes we're going to have to check our work, which is a calculator thing often, or mental math is another good option. If we look at number 11, this is already set up for us with the root isolated, so we're going to square both sides. I'm going to try to save some room. 2 minus x multiplied by 2 minus x. And so foiling this out, we're going to write down here below, we get 4 minus 2x minus 2x, and then plus, because a negative times a negative, x squared. We'll combine those terms together, and I'm going to rearrange while I'm at it. Bump x squared up front. Those make minus 4x, and then this 4 was positive. Now who's on the left side? Just 2 minus x, and so I'll carry that down and start moving things across if they need to. Minus 2 and the plus x. So this problem looks like we have 0 equals x squared. That makes minus 3x and then plus 2. And again, square root doesn't work, but you could complete the square, you could use the quadratic formula, negative b, plus or minus, all that jazz. But usually these questions are pretty nicely set up that they're going to get whole answers, and so whole answers are usually factorable. At least they should be factorable if you can think of the right combination. So what multiplies to 2 and adds to negative 3? Well, negative 2 and negative 1 satisfy those requirements. Put them over 1. And I'm okay if you go ahead and you understand that the answers will be the opposites of these. X equals 2, x equals 1. You know, we are far enough along in the year that it's okay to use tricks like that. But we do have to check our work. That is something in this section that we must do. So for 2, putting it back into 2 minus 2, I get the square root of 0 equals, and then 2 minus 2 on the right. Well, 0 does equal 0. Square root of 0 is a number, so 2 is okay. 2 works great. 1, if I do 2 minus 1, that's the square root of 1 equals 2 minus 1. And so 1 is equal to, well, 2 minus 1 is also 1. So that works as well. Both of these actually are good solutions. So you can't be prejudiced ahead of time of like, well, one of these is going to be a bad number. Occasionally you do this work and you get two numbers that both work for the original question. Okay, and so we went from x's to x squareds. It was pretty important that we did that because now we have both solutions instead of just one solution that we may have thought earlier. 12 looks awful, but if we kind of keep in mind that we're trying to isolate the roots, these two exponents are both roots. They just are written as fraction styles. And so we're going to go ahead and we're going to move one to the other side. It's probably nicest to move the subtracting group over because we get to add it to the other side when we do that. I'm going to go ahead and add 4 minus p to the 1/2 power. And so now my problem looks a little bit like this. I have 3p to the 1/2 equals, and then I have 0 plus that group, 4 minus p to the 1/2. Now what is great about this problem in particular is to get rid of those 1/2s, we know from the front, you kind of raise it to its reciprocal power, 2 over 1. So we're really just squaring it, which makes sense. If those were square roots, yeah, you'd square it. And so when I do that to both sides, the exponents for everybody literally just cancel out. And so I'm left with 3p equals 4 minus p, which is really easy. Now keep in mind I have p and p and p and p and p in my question, and I haven't gotten p squared anywhere. So for this problem, I'm not really introducing any extraneous solutions. If I add p to the left to get 4p equals 4, dividing by 4, I get p equals 1. With confidence, I know I can box this in because there was never any extraneous solutions from the beginning to the end. So only when you get a squared amount, or essentially when your exponent increases in size, that is when those extra answers sneak in. So this problem actually doesn't really belong on the back. One thing you might want to do with this question is put this in your calculator, because 1 in here and then having all these fractional exponents can take a little bit of time to check, and a calculator can check that for you really quickly. Well, you might think if 12 worked out so nicely, 13 might do the same thing because we have a third and a 2/3 as their exponents. But if we're going to go ahead and we're going to move this over to join the right-hand side, things might not cancel quite as well as they did on the left. So I'm going to leave this blank just so it's not gumming everything up, but I will write the 9x plus 1 group on the right-hand side. That's important. So we have x plus 1 to the 2/3 power equals, and then 0 plus, we have 9x plus 1 to the 1/3 power. Probably should be leaving some more space because this step of raising it to the reciprocal I'm kind of squeezing numbers in next to the equal sign. It can get a little messy. So now I'm going to go ahead and raise this to the same reciprocal. You cannot choose just 3 over 2 on the left and 3 over 1 on the right. That's not doing the same thing on both sides. And to be honest, we may actually have to switch this here in a second, because the lefts cancel and the rights sort of cancel, but what's left over? Is it a good situation to be in? I have 9x plus 1, to the 1/2 power. Well, what if I had maybe chosen a different exponent to go on each bracket step? Instead of choosing 3 over 2, if I back up, what if I had chosen to cancel out the right and do 3 over 1? Sometimes you have to try multiple different steps to see what works best. So the 3's cancel, that's good. It's maybe not as good as the other because the 2's canceled, so it seemed like more canceling would be better. But look what's left over. Earlier we had a 1/2 exponent. For this, now I have an x plus 1 squared. And then on the right hand side it's just 9x plus 1. Having a squared left over for your exponent is actually a little bit easier to deal with than having a 1/2, which is a square root, as your exponent. It's going to take more steps to get rid of a square root than it is just to FOIL this out. So as we know, x plus 1 is sitting next to its twin of x plus 1. Now, you guys, it may take you a few tries on a question like this to understand, like, oh, don't go that direction, go this direction. But with some practice, I think you guys can have intuition like that. So we get x squared plus 1x, and then plus 1. That's equal to 9x plus 1. I'm going to go ahead and combine like terms. X squared plus 2x plus 1 equals 9x plus 1. Moving stuff to the same side. This problem, we're moving things to the left because that's where the squared is. Usually I like to keep that positive. So this problem has a quadratic. It is x squared minus 7x and actually plus 0 because the positive 1 and the negative 1 cancel out. So how do I deal with a quadratic that looks like that? That's kind of interesting. Well, there are a few ways. You could technically x factor this. I think it's easier to actually divide out what is in common to both of those terms. And so they both have x's in them. And if you remember learning about quadratics, I said it's a little like fishing. You're going to fish out the thing that's in both of those lakes. And so I have an x that I divided out, which leaves an x from the first group, and then it leaves a 7, a minus 7, in that second group. And so you'll kind of notice if you x factored this, you'll get x plus 0 here, and you'll get x minus 7. It's the same thing. I just wrote my x plus 0 as a small little chicken nugget, if you will. So that just x by itself is the same thing. And now if we solve this, x is equal to 0, x is equal to 7. Some people are going to box that in right away, but you don't know if those numbers are good. So we have to check those. I will tell you, checking with the calculator and putting 0 in, putting 0 in, putting 7 in, putting 7 in. If you type those things in and you make sure that you have the right exponents and you don't get lost or put a wrong number in, both of these do work, which is surprising. You might think the 7 would be a terrible number, but 7 works great in that situation. Ultimately, when you press equals, you should be expecting to get 0. That's what the other side of this question said. So not an easy problem to do. Looks like we have 2 more problems before we wrap out this side on extraneous solutions. So number 14 is given to you with 2 roots. Kind of the same thing as what we've been dealing with, except that those were exponents. So we're going to move the roots to opposite sides to isolate them. We end up getting the square root of 3x plus 2 equals the square root of 2x plus 7. And I moved this because it's nice to add things across, so that way you don't have negatives in your problem. Now we're going to go ahead and get rid of the square roots by squaring. That leaves, since the square root's inside, 3x plus 2, no absolute value bars, and then 2x plus 7, no absolute value bars. And actually in this work, so the prior problem went to a squared power. This hasn't gone to a squared power yet, and I don't think that it will, because subtracting 2x and then moving the 2 across leaves us with 1x equals 7 minus 2 is 5. We don't really need to check this because we did not introduce a higher degree into our problem. We don't have the possibility of having fake answers sneaking in. Hopefully you guys are catching on and that makes sense by now. So the very last question is kind of a doozy. We're going to go ahead and get the root by itself. That's kind of our main concern. And so we're going to add 4x over here to the left. Unfortunately, negative 3 and 4x, they don't mix very well. So we're just going to write it out as two things together. And that's equal to the square root of 6x plus 9. Now we have to go ahead and square both of these. And you're squaring each side. So you can't just square individual pieces. This is foiling, not fluing. You'd forget the O and the I if you only squared 4x and 3 by themselves. Sometimes it is helpful to write out both groups. People tend to make less mistakes when they show their work. So we end up getting 16x squared from 4x times 4x. We get minus 12x. We get another minus 12x. Usually these two centers will be duplicates when you multiply by itself. And then plus 9. That is equal to 6x plus 9 on the right-hand side. And now we're going to go ahead and combine. As you've seen before, we get minus 24x. We get a plus 9. And we're keeping the 16x squared in the front. Now this problem looks a little bit bigger. We have an a value, okay, and that's going to make a difference when we choose what method we would like to solve with. So right now I'm just subtracting 9, which those cancel, which is interesting. Wasn't expecting that. We'll subtract 6x and subtract 6x. So my quadratic looks like this, 16x squared minus 30x, and that is equal to 0. So if I go ahead and think about this, this is a small question similar to problem number 13. And it is nice to divide out what you can. So I think 16 and 30 are both multiples of 2, and they both have some x's. So I'm going to divide 2x out of this situation. So if I have enough room, 2x gets divided out, and I am left with 8x minus 15 equals 0. If you had done the x factor, it would work. It might take you a while, but you're going to get these two groups. Now solving this is, sometimes people are a little rusty. So we're going to go ahead and we're going to take 2x equals 0. Well, that's not hard. You just divide by 2. So one of our solutions potentially is going to be x equals 0. The second solution comes from 8x minus 15. Setting that equal to 0 requires 2 steps worth of work. Adding 15 to both sides, 8x equals 15, and then dividing by 8. And this is why it's such a hard question when you x factors. One of these solutions is not the greatest. You get 15/8. Now you might be tempted to circle the 0 because you think it looks nicer, but actually putting 0 in, we can check this real quick. 0 going in for x and 0 going in for x, you end up getting negative 3 on the left, negative 4 times 0 is 0, so 0 plus, and then 6 times 0 is 0, and then you're left with the square root of 9. And actually, 0 as an x value, you end up seeing negative 3 is equal to 0 plus 3, which is 3. That is not a correct solution. on the flip side of this, people say 15/8, what an awful number. And so they would think that's the extraneous solution. But if you put 15/8 in for the x value, and if you put that in your calculator, you would end up actually getting the -3 that was required. And so 15/8, that is our solution. Not something people are going to guess just on their own. So you have to know the steps for solving these types of equations. Hopefully this video helped you guys see the value in kind of going through the steps and knowing exactly what to do and some of the strategies that are involved. But if you guys have questions, I'd be more than happy to answer them when I get back. But otherwise, you guys can definitely start your homework and try to get through some of those questions, and we can get you some help when I see you next. So thanks for watching, guys. Take care, and we'll see you next time. Bye.